Hello, everybody. This is TJ Willett, your moderator for today's webinar. Just wanted to give a few more minutes. I could see that there's some additional people that are still logging on, and I just want to give another moment or two for them to get into the software. So we'll be starting the broadcast momentarily. Thank you for your patience. Okay, we're going to begin our webinar presentation for today. I'd like to welcome you to our webinar presentation entitled Creative Strategies for Water Conservation Reuse. As I mentioned, my name is TJ Willits from Veolia Water Technologies, and I'll be today's moderator for you. And if you could advance that next slide, Ted.
TJ, it's not advancing.
Go ahead and click that window.
Yep.
Just bear with us 1 second until we figure out these issues here. Okay, can you try clicking now, Ted?
There we go.
Okay, sorry for that brief interruption. We're really excited today to kick off today's webinar presentation. This is the first webinar that we have in 3 weeks of live interactive webinars that we have planned here. You can see that there's a schedule listed on the slide. But if you go to our website, veoliawatertech.com, you could access our schedule and all the buttons to go ahead and register for our webinar series. So feel free to do that after today's webinar. And in addition to our live webinar series that we're promoting here today, we also launched our on-demand webinar library. We took all the webinars from the last year or two and we loaded them up on our website as well. And you can go ahead and access our website, click on the registration links and go ahead and watch some of those webinars on demand as you wish. Now, just some housekeeping items and webinar notes. You should be hearing me speak now, obviously. Questions about audio may be, should I use my mic or speakers? You could use either or. There's a login. You could click the button to access and listen to your headphones or your computer. Or if you click phone call, you could go ahead and dial in and listen over a cell phone or a telephone. Just the one thing is, because there's so many people logged on to the webinar, we muted your microphones automatically, so you won't be able to interact with your voice at all on the webinar. But however, we have the ability to take questions throughout the webinar. And to do that, you go ahead and to the right-hand side of your screen, you should see a questions panel. Go ahead and just enter any question that you may have in there. Feel free to do that throughout today's broadcast. And we're going to just inventory all those questions and try to get through as many questions as possible after the general presentation is complete. We will be offering participation certificates. A certificate will be emailed out after the webinar, about a 1 or 2 day time frame after the webinar, but that way you'll have a certificate if you need to use this to log for continuing education credits. And something that's a little bit fun, this is the first time that we ever did a 3-week live interactive webinar series. But what we want to do is get your input and feedback. So what we're going to do is put everyone who filled out the survey after the webinar. It's about a 30-second survey to go ahead, and we're going to put you in a drawing, and we're going to draw a name to see who can win an Amazon gift card, and we'll contact you after the webinar and let you know if you won. Okay, we're getting ready to hop into today's technical presentation. Just a little bit about Veolia. Veolia is a leading environmental company, global company. Our group, we are entitled Veolia Water Technologies, and we focus on three main pillars of our business. The first pillar is technologies. We have several technologies within our water treatment portfolio that we use to employ to help customers with their water and wastewater treatment needs. We also work in developing projects. We are an engineering and procurement expert, and where we bundle technologies together to allow customers to have really robust and creative water treatment needs. The last item of our pillar are services that basically complement the other areas of our business, but we have a wide range of services that we offer within this space as well. And we're going to transition now to our technical presentation. Our presenter for today is Ted Lawson. He's the Director of Strategic Marketing for Veolia Water Technologies out of our Industrial Solutions Group in Vandalia, Ohio. Mr. Lawson has over 39 years of water treatment sales and sales management experience, tied and coupled with product management, marketing management, and strategic marketing experience as well. He graduated from the University of Wisconsin with a Bachelor of Science in zoology and a minor in chemistry, and he currently resides outside of Philadelphia in Newton Square. So at this time, I'm going to hand the presentation over to Ted Lawson. Ted, are you with us?
I am, TJ. Thank you very much. And thanks everyone for joining to discuss what I consider to be a key global issue, and that is the water crisis. Today, we're going to talk a little bit about how we can navigate through this by focusing on water conservation, reclaim, and reuse initiatives, and hopefully help to reduce any associated risk in your facility and improving your environmental footprint along the way. So I'm going to start today with a little bit of a review on what we call the true cost of water, because it brings into play a lot of the parameters you might need to think and be understanding of as you embark upon any water initiative that'll help create the overall value of what you're trying to accomplish. And hopefully by the end of today, if you haven't already, I hope that you'll be more inspired than ever to take some of what we've talked about and put it to work in your own facility. That said, we at Veolia Water Technologies are always here to help in that regard. So what's all the hullabaloo about water conservation? I mean, historically, the predicament here in the US is that we've traditionally treated water as a commodity. So for the most part, I believe Americans can relate to this quote. With few exceptions, we treat water as a commodity. We thus often overuse, undervalue, and abuse it. Compared with many geographies around the world, our water is relatively inexpensive. And even with significant recent increases from both water supply and wastewater municipal charges around the country, we still have access to some of the cheapest, most abundant fresh water in the world. But that's not to say that water-related risks haven't already materialized. So I thought what I'd do is just run through 4 brief areas here that encapsulate one of the driving forces behind water recapture in your plants. First is operational risk. So in that regard, what is the value of water risk related to the ongoing operation of your facility? You know, at a minimum, how efficiently is the water being used? How efficiently is it being supplied? How efficiently do you have access to it? How is water sourced, treated, controlled, and administered? And additionally, and sometimes more importantly, how is it performing? Are water impurities creating deposits which increase downtime in your facility or inefficiencies from a heat transfer standpoint? Or is your water corroding key system components which require replacement on a regular basis? At the other end of the spectrum, how much risk does your current water source itself provide the plant? Is the quality of the water consistent? Is the quantity of it enough? What if your plant is in the fortunate situation where they have to or want to expand? Does your current water infrastructure allow you to embark upon those ambitious plans? As far as financial risk goes, not just limited to the price of water or to the water treatment chemicals or the equipment used to operate or utilize the water, but the bigger picture of the finances surrounding the water, equipment shutdowns, maintenances, replacements, safety issues with your employees, production impacts on product quota, and even so far as to say your customers' feedback on what they're getting from you that may be a result of water impacted issues. The impact on your P&L can be considered and should be looked at as a total cost of ownership from both a CapEx and an OpEx perspective. Thirdly, regulatory risk. What impact does the use, treatment, and/or discharge of your water have on your environmental footprint and even on your NPDES permit? Is your system capable of providing for your production needs while satisfying the regulatory requirements that you have to abide by? Can your plant afford any water-related non-compliance issues? In most cases, no. And lastly, the reputational risk. And sometimes we overlook this, but more a part of the third leg of the sustainability stool, more or less referring here to social license to operate, related to the cost of water used in your plant, akin to safety, environmental good stewardship. Many times you can tie into this a huge impact on your plant's public relations in your community, your ability to even attract and retain good employees, and lastly, in some situations, even the value of your stock. So let's talk about the true cost of water. Well over a decade ago, as members of the World Business Council for Sustainable Development, Veolia developed what we've called the true cost of water model. The model outlined all of the areas that impact its cost, the cost of water usage in a production plant. So first we talk about the direct costs. Now these are the costs that we're normally associated with and are pretty familiar with. These are the cost of simply obtaining water, the cost of investing in water, either from an OpEx or a CapEx perspective. However, there are a significant amount of indirect costs that are related to things such as insurance and legal activity, litigation surrounding water-related issues. I know in the news we've seen quite a few of those over the past few years. Being the father of an environmental risk manager for a large insurance company, my daughter continually reminds me of the horror stories she sees in this area of the true cost of water. They can truly be significant. Lastly, as mentioned on the previous slide, there are 4 key areas of financial risk associated with the operation, finances, regulations, and reputation of your facility. So we won't go through those again. But without looking at water in these 3 areas, you cannot obtain a true cost of what the value of water is for your plant. Now, as we get out and work in the community with our associated people, as well as our clients, I'm encouraged to see that many clients, particularly those with a number of operating plants across either national or international boundaries, are beginning to benchmark their water consumption and/or their water efficiencies for their facilities. Now, whether this is done across countries, across divisions, across states, or even across departments within the same facility, benchmarking can really help you develop an outline or a footprint to develop your water strategy or your water plan from. Benchmarking can show you what is achievable, give you insight as to how to make improvements, and help you to set realistic goals and objectives. Many of the water efficiency factors that we look at when we audit facilities are listed here on this slide. As you can see, some require simple data mining, such as water costs, quality, volume information. We know where to go and get that information and typically who possesses it. But until we understand and examine factors such as process design, process variability, housekeeping, efficiency issues, we can't really come to a viable conclusion on what our true water footprint is, where we should spend our time looking for opportunities to improve it, and how substantial these opportunities might be. Again, working off that true cost of water model that I mentioned earlier, recognize that each of your plants will have different scenarios and priorities. And each of them will create your own individual drivers as to why, when, and where you should probably focus your water reuse strategies. A few of these reasons, again, the operational risk, reducing the risk of a plant shutdown due to any water issues. Secondly, when you look at the plant infrastructure, the use of water costs you money in time, people, materials to maintain it. Your total waste should be looked at as it relates to water. And there's a cost, obviously, to that total waste perspective. Beyond the simple loss of water volume and treatment costs, water recovery might make sense because the waste being created contains valuable impurities. Those impurities can take the form of energy, BTUs, in hot water. It can take the form of a lost production raw material or product, which has value that you want to recover. So there are many other additional areas that do, again, enhance the value of the water you're using. Next, reuse or reclaim initiatives might be prompted by plant or even corporate, and in sometimes municipal or state initiatives related to water reduction or discharge. Keeping your plant compliant with any of these objectives at times is mandated. And overall, reducing the water footprint can be important to your plant as well, because you want to include a positive impact on your employees, public relations, as I mentioned earlier, and the communities that you operate in. You want to be a good neighbor. And then lastly, in many cases, investment in water initiatives can help your company avoid, or in some cases reduce, the need for CapEx investment. And obviously that can help the balance sheet and keep your financial managers pleased with your efforts. A little bit about water reuse guidelines. And I say that because there really isn't a lot to learn or a lot to research. There has really not been a single framework for guidelines surrounding water reuse in the United States. The first important document that was really introduced was issued back in 2012. And there were some very, very broad guidelines for water reuse, which I'll show on the next slides. But these guidelines were based on water reclamation and reuse practices in the US, specifically directed toward the states who have not yet either instituted them, supported them, or gone to any more level of detail in rolling out localized guidelines that you in industry can follow for the efforts that you want to put forth into your water reuse initiatives. So here's an example of what was included in those 2012 guidelines. And as you can see from an industrial reuse standpoint, the only two types of applications they were looking at were once through cooling and recirculating cooling towers. Now, while those are very large volume applications in many cases, they are not the only applications. And as you can see, by meeting very broad and very simple guidelines on pH, BOD, suspended solids, etc., with a minor chlorine residual, you could very easily fit waters into those types of applications. When it came to indirect potable reuse, the basic guideline was to meet drinking water standards, which of course can be obtained very easily through simple treatment and post-treatment in your respective sites. But as you can see, outside of this, the lack of guidelines is a key missing piece of component in the equation that we need. So what are we trying to do here? Well, as a large water treatment company, matter of fact, the world's largest water company, we're trying to work with our clients to reduce their overall water footprint. So first and foremost, identify opportunities where we can conserve water, reclaim water, or reuse water in your plants. Secondly, determine where we can find the most sustainable combination of equipment, chemistry, and services to take advantage of those opportunities. And then utilize the total cost of water model to come up with the true ROI that you have available to you should you embark upon and execute any of those projects that you've outlined in your efforts. We view efficient water management as having three integrated components. It's been our experience that the low-hanging fruit in many plants can be found by simply optimizing the use of water that you're already using. Attempts to conserve water and optimize the use of the water that you are using right now can return big dividends. So our advice is that you work with your water treatment provider to really, for lack of a better phrase, tighten up your belt. There's a number of areas you can immediately improve upon under the consumption of water used in your facility. These are areas such as improving or increasing the cycles of concentration in your steam boilers. Likewise, cycles of concentration in your cooling system. The operation of utility pretreatment equipment. Work on things such as regeneration schedules and the efficiencies of those regenerations. Production process filtration backwashes and rinses. Housekeeping and cleaning procedures, which utilize a lot of water. Production quenching, rinsing schedules out in the plants. Are there modifications to your current chemical treatment program that can be made to stretch and use the water further than it is currently being used? And can preventative maintenance programs be instituted for any water treatment equipment to optimize their operation and produce and manage the quality and efficiency of the water that they produce? So all of these and many more areas can fall under that conservation pillar of an integrated strategy. Next, are there water streams being used in your plant that might be able to be reclaimed before discharge to be used in another application, which might have somewhat of a lower value within the plant hierarchy, but still be able to fulfill a volume of what otherwise would have to be freshwater use? For example, can once through pump seal water be collected and redirected back into a secondary usage with minimally increased costs? Can utility pretreatment rinse water be captured before the drain and used somewhere else in your plant? So the second bucket or pillar of the integrated strategy is looking for streams that already exist that could be reutilized or redeployed someplace else in your plant. And then lastly, many plants are designed to simply use their water and send it to drain. But there are many large water using processes in your plant that, if properly retreated or altered in quality, might be able to be reused in a higher quality application in your plant. Again, production rinse waters, such as mentioned before, cooling tower bleed, utility backwash and rinse, once through applications. The list goes on and on. But by taking any of those quality waters and improving them through pretreatment, you can also find higher value applications for those types of water. So once you've got a firm understanding of this three-pillared approach, which we just talked about, conservation, reclaim, and reuse, the next steps around a few key basics. Number one, first and foremost, you do need to develop the framework of a plan, and the plan should have a sponsor, with an executive sponsor being most helpful. It should have cross-functional team members on it, people that use the water in the departments where it's most critical, people that control the water and manage its use through the utilities in your plant. And the plan should also have key objectives, timelines, and a budget, or at least have access to a budget should you need any money to initiate any components of an overall plan that could turn a positive return on investment for your plant. Secondly, estimate what in your plant is achievable or recoverable versus what isn't. And by that, I mean, there's just certain water streams in certain plants that you can't recover. Evaporation from a cooling tower being one. Secondly, ingredient or raw material water that goes into your process. Obviously, you're not going to get back those volumes from your plant. Thirdly, be consistent. Go through the conservation, reclaim, reuse checklist for every water stream that you study. Tighten it up first, look where you can reclaim it second, and then look lastly whether you can reuse it by transforming it into a different quality water. And lastly, and sometimes the most confusing component of moving forward is understanding the complexities of your plant. Wastewater recycle at the end of the pipe, when the water leaves your plant, can be done. But at that point, your waste streams have all commingled. They're many times complex and difficult to treat. And with that complexity becomes much cost. Many times, if you look upstream in your plant and reclaim waters from a point source perspective, it's easier, it's cheaper, and you'll see the impact quicker. Secondly, understand that each of these water streams, because they do lead downstream to a bigger pipe eventually, they do interface and impact with other streams. So you need to look at, when you do something, the quality and the quantity of what you've done. And the last bullet, which is quite just common sense, follow scientific procedure. Do not change too many things at once, or you won't be able to understand the impact that any of your changes have had. In many perspectives, that's why these initiatives many times take a long time to go from square one to the finish line, because you do need to stop and see what impact you've had with each step that you implement. And I can't stress that enough. So how do you start? Where do you look? First and foremost, prepare a water balance. You have to understand everything, water in to water out and everything in between. After you've got done mapping the water balance in your plant, and sometimes part and parcel, conduct a thorough plant audit. Now, this is taking your water balance and literally going to each unit of operation in your plant and going through a thorough analysis of how that water is being used, how much of it's being used, what the quality of that water is that's being used, how efficiently it's being used in that operation, and what type of waste it's generating. The third step is then reviewing technical options that you have. And we understand that we've got a pretty thorough and pretty robust portfolio of technical options for our clients. Sometimes some of them do or do not fit into your individual situation. But typically, technology can help to enhance your efforts, particularly once you get beyond the conserve and the reclaim steps into the reuse portions of your projects. And that's where you can then sit in step 4 and determine the best solutions, taking all of what you've learned, all of what you've documented through steps 1 and 2, all of what you've learned in step 3, and putting it together into a plan in step 4. So what should you expect when you go through an audit? Well, first and foremost, you have to have an on-the-edge engineering approach. And by that, I mean, you're not looking at how your production process looks from the production side. You're looking at it from the utility side. The same thing is said in the utilities. You're looking at it a little differently than a traditional daily water treatment person might look from a service perspective. You want to study everything from water in, from the time it either leaves your source to the time it leaves your plant, and every application in the middle. Look at it from a non-traditional perspective. Don't look at how you can throw more chemical at it. Don't look at putting in another piece of equipment. Look at the options. Look at the opportunity costs and determine what the best integrated approach is. Gain a thorough understanding of the water usage in your facility, and you will be the one that will be able to play chess with that and understand where your next move might be and how you might be able to make the biggest input. Vet those solutions with people that know. Vet those solutions with technology providers, with your water treatment folks, and with your management team. And see how they fit with both existing and planned potential issues or problems. And from that, as a result, tie in your water initiatives with a strategic, technical business plan that fits with the infrastructure requirements of your company. All right, so if you remember, we had the 4-step process. Going back to step 3 was evaluating technologies. So I just wanted to run through these, not in any great detail, but just to go through the steps that you might have to embark upon in a reuse process development and some of the options that you might have in those processes. So the first step is if you've got a waste coming down a pipe, you have to make sure that you remove the solids from it. Those solids could be a biological solid that's high in BOD, COD, suspended solids, have pH fluctuations. We've got shown here 3 different technologies. They just happen to be Veolia's, by the way. The first is our biophane high rate anaerobic technology. The second is our memthane anaerobic MBR. And the third is our MBBR pack. These 3 technologies are excellent at taking high biological waste, which might be present in a food and beverage plant. It could be present in an organic chemical producing plant, or it could be present in many respects in municipal operations as well. I shouldn't leave out, but pharmaceutical wastes also have a keen fit for these types of technologies. In non-food and beverage facilities, on the bottom of this slide, we have our ActiFlow clarifier listed. If you don't want to float things but want to settle them, if you don't want to digest them, if they can only sink, the ActiFlow clarification process is well adapted to these types of applications. It's a compact, sand ballasted upflow clarifier that allows it to be built with a very small footprint. And when it comes to reuse and reclaim situations, many plants don't have the space for these types of applications. So it helps to be able to have a smaller footprint. On the top of the slide, much like the digestion technologies mentioned on the previous slide, dissolved air flotation can be used where you've got high BOD, COD, and TSS. The Veolia Hydroflot technology is excellent because it does have a modular design and a patented air injection system that enhances the float that you get, the removal of these suspended solids with, again, a smaller footprint than traditional technology. The next step that you would be embarking upon would be filtration. So now we've got all the large particles out of the stream. Now you need to get down to a smaller level and filter out smaller particles. On the top of this slide, we have a picture of a disc filter, which is Veolia's Hydrotech disc filter. This technology allows you to get much more granular on a particle size basis. It's excellent for use in cooling tower side stream filtration and both wastewater and water reuse systems from a polishing standpoint. The unit operates on a concrete pad. It can be operated with a gravity flow, very easy to operate, and has a automated online backwash system that doesn't require much attention at all. On the bottom of the slide, we move into more of a fine membrane system, one of Veolia's UFlex ultrafiltration units. These units allow you to get down to about 10 microns of particle size. So there you're looking at removing very, very fine suspended particulate. You're looking at even removing turbidity, some bacteria and viruses, and reduction of some of the larger organic compounds that might be in your waste. It's great for putting upstream of further membrane systems such as ROs because you're protecting those membranes from fouling and from scaling through the particles that are removed in the ultrafiltration unit itself. A third type of filtration, which is more common, is media filtration. And media filtration can be either multimedia or an activated carbon filter. Both are used quite commonly in industry and in municipal applications. Multimedia, comprised of 3 different sized media, is used very nicely for a lot of different applications throughout industry. And activated carbon has a little bit more of a specialized application, such as dechlorination. Many processes in your plant might not allow a positive chlorine residual because of process requirements, or upstream of a membrane system that does not allow chlorine for long-term membrane life. And similarly, activated carbon can be used to absorb and remove organics from a water stream, where those may be harmful or impact water quality and utilization downstream. So 3 different types of filtration. Now, once we've taken the solids out and filtered everything down to a specific level, then we look at deciding whether we need to remove any minerals. The most common type of mineral removal is standard sodium zeolite softening, as is pictured here on the top of this slide. The IonSoft units pictured here, very standard units regenerated with salt and help to remove calcium, magnesium, and iron, which will deposit or scale, as we call it, very high heat areas in any process, and can help to produce a soft water that can be used and multi-purposed in other applications in the plant. These units can also be provided as dealkalizers or demineralizers if those are your needs for more of an ultra pure approach. On the bottom of the slide, we look at reverse osmosis technologies. And now you're getting to a point where you're starting to remove 98 to 99% of the total ions present in a water. In essence, we're not producing impure water anymore. We're producing HOH, as I like to call it, another way of saying H2O. This water is run through very small pores in a membrane and creates a very pure water effluent. Now, over the past decade, RO technology in industrial applications has grown exponentially and are often used in water reclaim and reuse systems. So now we've got the water down to as pure as we want to get it. What do we do with all the waste we've created? Well, first of all, be aware that we have created waste. Every unit that we've talked about has some type of waste, either a sludge, a float, solids, a backwash, or some type of a waste. We need to determine whether we want to go further. The last step in the process would be to determine whether we need to concentrate sludge any further and or remove any sludge from the final waste effluent. So evaporation and byproduct recovery is still a final step, or could be a final step in the process. In many situations, you may have a byproduct in that waste sludge that needs to be recovered. You may be under some pressure from your local community or your local management team to go through a zero liquid waste scenario and truly eliminate water from being discharged from your plant. Or it may just be a total reduction in waste disposal volumes. Let's face it, tipping rates with the waste disposal companies are not going to be going down in the future. And by reducing the total volume of sludge that you dispose of can be looked upon as being positive on your P&L. The Evoled units pictured here are very good at recovering a high quality condensate from a water containing sludge to reduce that overall volume and recover the last volumes of water that you can in your process. And then again, moving water back into a plant, depending upon where you want to take the water from the process that you will have designed based on the opportunities that you have identified. Disinfection could be the last of the steps. So depending upon where you're taking that water, how corrosive it can be, whether there's any byproducts in the water that need to be killed. If you're looking at producing NSF quality water, depending upon what pH conditions the water is, and other such things to consider as mentioned in that list there. There are many different options, from chlorine derivatives to chlorine dioxide, peracetic acid, and ultraviolet light. So many options that you need to consider and be aware of as you go to that step in a reuse system. All right, so far, you've mapped out your facility. You've qualified and quantified your water footprint. You've gone through the audit. You better understand your plant now than you ever have. And you've tightened your belt. You've looked for opportunities to conserve where appropriate. You may have already found 10 or 20% reduction in your total water consumption. It has been our experience that this is not uncommon. So now what do you do? What do you do once you've tightened your belt? Where do you go next? What are the next steps? Our advice is that you might look toward categorizing the type of water that you need in the plant. And by that, I mean, what quality requirements for each water that you use in each application do you have? And typically, they can be bucketed or commonized into 2 or 3 major types of water, and they're going to be individual for your plant. The first question you would ask is, once you've agreed upon and identified what those types are, does that type of water already used, is it already being used in the plant, and is it being wasted anywhere? And if so, can I reclaim that water back into another similar application, as we talked about previously? If it doesn't already exist in the plant, how can you create that type of water from other waters that are being let go, discharged, or sent to drain? What technologies are needed to develop this type of potential reuse? How much do they cost? How do I document the total cost of that opportunity? And will it impact any other changes that I'm making to my overall balance or footprint? So we've taken it now one further step. Now we're into reuse. We're looking at truly getting down to where you now have to look at investment being offset by savings to document and justify the initiatives that you are now starting to identify and execute. I thought I'd finish with just a couple of common case studies that we've developed, that we've seen over the years. And again, these are specific to certain types of plants that may or may not fit what you're dealing with at your facility. But on the other hand, you may see some things that are quite common that you may be able to take advantage of as you go through the balancing and auditing of your plant. The first was a refinery out in the Midwest that had some pretty keen, but pretty well-known and unfortunately very stringent water objectives. Availability had always been a problem for them. They had quality and quantity fluctuations, which you cannot have in an oil refinery. And those fluctuations threatened both the reliability or the operation of the plant, as well as its efficiency. There was no real water sustainability plan, and trying to balance between the daily operation of the plant and longer term goals and aspirations of the plant were very difficult. So we were brought in to study the water balance and come up with a plan. Well, the plant produced about 2,000 gallons GPM of water, 1,772 gallons of water. We brought in the mobile water unit to put side stream in parallel with the cold lime softener. And what that did is it allowed the cold lime softener to produce a more consistent output and actually enhance the total capacity of the pretreatment so that the refinery could rely upon the water that it was being sent. The next step was to improve the operation of the multimedia filters. And that turned out to be a huge return back from the plant. First and foremost, they eliminated the need for $150,000 capital expense because of the improvements that were made in extending filter run lengths, improving the performance and the output, reducing pre-filter and membrane loadings downstream. We also eliminated the need for acid feed, which of course was a huge savings from a safety perspective. Now, somewhat related to the multimedia filters, but downstream of the filter project, the filter backwash was still a very large flow. As you can see on the slide, 83 gallons per minute. A settling tank was installed to capture that backwash. After the settling of the backwash occurred, a lower TSS water was produced, and that was sent to the cooling tower as makeup. It reduced the need for fresh water to the cooling tower and reduced the amount of wastewater generation to the waste treatment plant by 83 gallons per minute. I'm sorry, by 83 minus the 5 that we generated, and produced an additional 79 gallons per minute of reuse water. So 83 gallons from the MMFs, 4 gallons from the bottom of the settling tank, and 79 gallons sent to the cooling tower. Similarly, RO reject, which previously had produced a 150 gallon per minute stream of reject that went to the wastewater treatment plant, was sent through a bank of high efficiency softeners. That reduced the hardness level of the effluent from the ROs, and that water was returned to the cooling tower makeup as well. So this produced over 73 million gallons per year of reuse water to the cooling tower that otherwise would have gone directly to the wastewater plant. With all of that happening, a change was made in the boiler water chemical program, which reduced the blowdown by over 38%, not only reducing wastewater generation, but also reducing the loss of BTUs that were emanating from the, and chemicals actually, that were emanating from the loss of the higher blowdown levels. And then lastly, with all the changes in makeup to the cooling tower, the change was made to the chemical treatment there as well. And that resulted in, as well as a chemical reduction, but also a 33 gallon per minute reduction in cooling tower bleed. Some significant changes with significant results. The waste treatment effluent dropped from over 500 gallons per minute to less than 250. If you look at what that means, if you look at the total cost of water of those initiatives, the first fact that needs to be realized is that this was about a 2-year project. It was done in phases, and it was done so that each step could be monitored, analyzed, and the impacts understood before the next phase was implemented. So the total water saved was 139 million gallons per year. That's a tremendous amount of water. It only represented a 13% decrease in total water flow, but it was a total water flow of 265 gallons per minute. They did have to invest in steps along the way. Total investment by the refinery was about $1 million. But look at the ROI, it was only less than a year, 11.1 months. And I would be confident in saying that most of your management teams would love to have an 11-month ROI on CapEx projects that they undertake. Maintenance was also reduced. When this was all said and done, the plan that was put in place supported the 10-year refinery expansion. And most importantly, the efficiency that they produced their product dropped from, that should be, I'm sorry, we've got a decimal point error there, dropped from 16 to 1 down to 14 to 1. That puts them in with world-class competition in the refining industry from a water efficiency standpoint. The second case study, a vegetable producing plant. They were producing about 2 million gallons per day of wastewater flow, and the plant had both short-term and long-term objectives that were pretty substantial. A 10% immediate reduction in water consumption by this year, and a 50% reduction 5 years down the road. I want to focus on this because there are a lot of initiatives here listed on this chart that are simply water conservation initiatives. So by tightening the belt, as referred to earlier, this plant was able to reduce short-term 13% of their total water consumption. So a water audit and balance was completed. These 5 key applications were identified, and as you can see, the largest of those was increasing the cooling tower cycles, and that was done so by putting them on a Veolia zero liquid bleed system and cutting off 126 gallons per minute of cooling tower bleed that would otherwise be going to waste treatment. There were also 3 other midterm opportunities that would have required additional testing and some investment that will add to that by an additional 12% of overall water consumption. And longer term, looking down the horizon, a capital expense project to put a full flow reclaim system on the waste treatment effluent should be responsible for reclaiming another 50% of the remaining wastewater flow. So again, starting with tightening the belt and moving toward initiatives after that, you can see the types of impact that you can have and possibly some of these you can see in your own facility. The last example I'll use was again in another food production plant that wanted to turn off their waste pipe and bring back their entire wastewater flow into the plant. Flow is about 1,200 gallons per minute. We need to first install an EQ tank to allow the wastewater effluent to equilibrate. Going again through the process we outlined earlier from a technology standpoint, by installing a disc filter, that entire flow of water was allowed to reduce the suspended material in it to a point where we could take that water and put it through a sodium zeolite softener and produce softened water. At that point, 350 gallons of that water gallons per minute of that water could be sent to the utility areas for use in the boiler house upstream of their RO units. The remainder of the water, the 620 gallons of the softened water, was sent as pre-treated water to a RO unit, which was then sent through a chlorine dioxide generator and back to the plant as non-contact NSF quality sterilized water. Remaining water that came through backwash for both the softeners and the ROs went to the cooling towers, and the cooling tower program was changed to fit with the new makeup water quality and prohibit any inefficiencies in the use of that water throughout the plant. And then any water coming off the cooling tower immediately was sent back to the influent from or to wastewater treatment. However, an option is there to, in the future, look at evaporation as a means to eliminate the last streams of water that we can get and return even more back to the plant. However, at this time, with their operating conditions, the evaporation step was not as cost effective and will not be viewed as part of this overall program. So let's just summarize what we've talked about. We've talked about a couple of key factors. Each application, each of you that are on the webinar here today will have a different set of circumstances, and your needs and approach will have to be different. But in every one of your cases, you will need to develop a plan. And that plan should have in it an integrated strategy that first and foremost looks at conservation, reclaim, and reuse for every opportunity that you identify, that you look at the conservation, reclaim, and reuse through a combination of equipment, chemistry, and service. And then also, having done that, make sure that what you do is understood and you can document it on your water balance and understand how it alters the detailed audit that got you to that point. The final step is then making sure that before you go to management with ideas and/or opportunities, address the total cost of water. You may not have opportunities to have access to all of the financial information, but if you put enough of it into each of the opportunities that you identify, you will have turned enough heads that people will start to understand that there is true opportunity here to help improve the plant. And lastly, work with your water treatment and equipment partners using the scientific method. Don't change too many things at the same time, and understand that sustainability only exists if there's a positive ROI in the applications that you're looking at. And that is truly the end of what I have. TJ?
Great, thanks so much, Ted, for that presentation. We're going to close at least the initial presentation, but we're open for questions. If you go to the right-hand side of your screen, again, there's that question panel that you could enter a question. We'll try to get as many as possible. We have a couple coming in now that we'll try to get to, but if you want to take a few moments, fill out your questions for Ted, and we'll try to prioritize them as much as possible. While those are coming in, we did get one question earlier on in the presentation. It's a common question, but it's a question about semantics. Ted, can you comment a little bit about the difference between some of the words you use, like reclamation, reuse, recycle, and really what those mean in terms of, is there an industry standard, or what is sort of the textbook terms of what those mean?
Oh, thanks, TJ. It's a great question. And I apologize if I've confused anybody with my overall commentary, but there is no true definition, so to speak. I mean, obviously, conservation is a name or a word in and of itself. I don't think that requires any further discussion. But when you get to reclaim, reuse, and even recycle, many of those terminologies can be used interchangeably. Within Veolia, we like to call reclaim as an opportunity to take a stream of water with very little investment and turn it back into, or reclaim it as, a more usable or secondary used stream of water. If investment needs to be made, then we typically term that as reuse. So we're transforming that water into a form which is then reusable someplace else back in the plant. Lastly, we typically only refer to recycle when we get to the effluent pipe of the final waste treatment plant. So in a nutshell, that's what we do at Veolia. It doesn't mean that you and your teams have to refer to them the same way, but that's how we refer to them.
Great, Ted, thanks. Another question that we have here is it's relating some technologies, and the person asking said, if we want to compare RO and forward osmosis, which one is more energy efficient? Would you happen to know that? And another part of that question is also, what is the difference between quality of permeate in these two processes?
TJ, I'm sorry to say I do not have an answer for that, but we certainly do have a talented team of engineers and technical support people that can get those answered. I will say one thing, that it's an excellent comparison to make, and in each individual situation, that may or may not be the way to go. So we will be certain to make sure we log who filed that question and get back the answer that is most appropriate to them.
Another question that came in here is you talked about that refinery wastewater refinery application at the first case study. You mentioned that you had a mobile unit on site there. Can you talk a little bit about what that mobile unit was doing, what the process was?
Sure. If you recall, the refinery or the site was having problems not just with quality or quantity of water, but quality of water. And anybody that's ever operated a cold lime softener will understand how that might happen. It's a very difficult piece of equipment to maintain consistency with. So with the ongoing demand in the refinery for a given quality of water, by expanding the capacity through a mobile clarifier, it enabled the cold lime softener to begin to work within spec and produce a better quality effluent. As far as the mobile water clarifier itself goes, Veolia does have a fleet of mobile trailer-mounted upflow sand ballasted clarifiers, the ActiFlow technology, that find application in situations like that. And the ActiFlow mobile units can handle flows up to 1100, 1200 GPM for larger trial type situations and applications.
Okay, another question goes back to the true cost of model. The presentation was mainly industrial focused, but can you talk about how the true cost of water might act for a municipality or for a public sector?
Sure. I don't think the parameters will change, to be quite honest. The degree with which direct costs impact a municipality would, of course, be different than an industrial site. You're talking about cost of pumping water into your treatment facility instead of buying it from a municipality as your influent in an industrial application. I don't think there's any difference in indirect costs when it comes to ensuring the quality of the water meets any guidelines or requirements from a governmental standpoint. So you're still going to have quality and risk related issues that stem from that, from a compliance standpoint. And thirdly, depending upon the quality of the water that you're bringing into a municipal plant, whether it's highly organic water from Central Florida, highly scaling water from the Midwest. You're going to have different costs related to the management, treatment, and support of that water. So I think the model still holds true, independent of whether you are in a municipality or in an industrial application.
Okay, great. I think we have time for one final question. It relates back to the ActiFlow. The person asking said, you mentioned that it required less area, but also does that mean less CO2 emissions? And do you have a CO2 comparison between ActiFlow and a conventional clarifier?
Well, excellent question. I do not. I will have to get back to you on that after conferring with our technical people.
Okay, and I want to keep to our time. It's about 3 o'clock Eastern time here. We ran a little bit over, so we thank you everyone for staying on for the question part of this webinar. Just a reminder, if you could take that survey when you log out of the webinar, that'd be great. It's going to help us improve these for the future events going forward. And again, feel free to access our website to see what other webinars we have going forward. We're really excited for it. And then lastly, I just really want to thank our presenter, Ted Lawson, for all of his time and his preparation for today's presentation. It really meant a lot for that to share his knowledge with all of us here online. So at this time, we're going to conclude the webinar, and I wish everyone a safe and amazing day.